Hello everyone, I am Gonzalo and I'm here to present our recent work on assessing image and text generation with topological analysis and fuzzy logic. This is joint work with Julian and Christoph Meinl at Plattner Institute. In this work, we propose a new metric called Fuzzy Topology Impact or FTI, and this metric is based on UMAP's topology representations. These representations come in form of a graph that uses k-nearest neighbor to construct a weighted directed graph where each weight represents a probability of the existence of a given edge, meaning it is related to fuzzy logic in this sense. Our metric can be used to retrieve two interpretable values which are correlated to sample quality and diversity. Since we do use this fuzzy logic information from the graph, our approach is finer grained than current approaches. Our code is available online at GitHub, so please feel free to check it out. So let's go through a quick example so we can better understand our metric. Let us consider four original points, where each point represents an embedding from a pre-trained model. In our use case, we used Inception v3. Then we use UMAP to create an original weighted directed graph from these original points. And we used in this example k equal to 2. So this means that each point will have a weighted directed edge to its two closest neighbors. Since all of the nearest neighbor points are at the same distance from the original point, all of the edges have the value of x. Now let's consider a new point that we represent as an empty circle in this example. If we reconstruct and update the previous graph, we'll have a new graph because this new point is within the closest neighbor set of at least one of the original points. On the other hand, if this point will not be within this set, then this point can be seen as an outlier point, as we show in figure B on the right, and this will have no effect on the updated graph. So our metric looks at this drop of the average probability of existence of the original graph, which we represent as impact, to determine how close the new point is to the previous original points. Now let's take a look at another tie example, but this time with a randomly distributed set of original points represented in the left column. Let us first consider the two neighbors in the top row, which means that we use KNN with k equals to 2, both for FTI and impar, which also uses KNN to create its scores. In this example, warmer colors mean higher impact or higher scores, and cooler colors means lower impact or lower scores. So the middle and right column represent the score or impact that a new point would be given if added at a certain position on this plot. We can clearly see that our method is much more able to associate the correct score or impact to a new point than impar, and this difference is even more clear if we augment the number of neighbors. Similarly to existing metrics, we can use our approach to independently evaluate a new set in terms of quality and diversity. To achieve this, and in our use case, we simply measure the impact that on average a fixed sample has in the real data graph if we want to assess the quality. Or on the other hand, we swap these sets and measure the impact that on average a real sample has on the fake data graph to assess diversity. We evaluated our method on several data sets and models across image and text generation. Focusing on image generation, we compared against widely used metrics such as inception score, FID, PRD, and impar. Overall, FTI showed to be more accurate when evaluating noise corruption, mode dropping or mode collapse, as well as mode addition and invention. These results also translate to the textual data where we assess language generation models and we show a higher correlation to human evaluation on these. Thank you for your time.